Alright, students, let us solve some problems of dynamics. In this case, explaining problems related to the Newton's law of motion. Our first problem says that a proton moving in an electric field has an equation of motion, R equal 4.0 times 10 to the 4th t, I plus 2.0 times 10 to the power of 4t minus 2.0 times 10 to the power of 5 t squared k minus 4.0 times 10 to the power of 5 t squared k, where r is the distance in meters and t is the time in seconds. The proton has a mass of 1.7 times 10 to the negative 27 kilograms. The question is, what are the components of the force acting on this proton, and what is the magnitude of that force? Well, we have here the equation of motion. So we know that if we know the position of the proton, we can find, using derivative, the equation of velocity and the equation of acceleration. So to solve this problem, we're gonna find the equation of the velocity, that is the first derivative of the position, respect the time. So we're gonna find the first derivative of the equation we have over here. As you can see, the first derivative of 5.0 times 10 to the 4t will be 5.0 times 10 to the 4th. I. The first derivative of 2.0 times 10 to the 4t will be 2.0 times 10 to the 4th. And the first derivative of negative 2.0 times 10 to the 5th t squared will be 2.0 times 2 times 10 to the 5th t. So it will be minus 4.0 times 10 to the 5th t. J minus, and then the first derivative of 4.0 times 10 to the 5th t squared will be 4.0 times 2 times 10 to the 5th times t. So it will be 8.0 times 10 to the 5th t k. So this is the equation of velocity. Now we know that the acceleration is the first derivative of the velocity. So we say that acceleration, and put vectors here, is dv dt. So the first derivative respect the time of 5.0 times 10 to the 4i would be 0 because it's a constant. The first derivative of 2.0 times 10 to the 4th dt would be 0. And the first derivative of negative 4.0 times 10 to the 5th t would be negative 4.0 times 10 to the 5th. J. And then now we have sorry, the first derivative of 8.0 times 10 to the 5th t, that is going to be 8.0 times 10 to the 5th k. Of course, we have a positive sign in front of the parentheses, so working a little bit on this expression, we have 0i plus, sorry, not plus, not minus. So minus 4.0 times 10 to the 5th power j minus 8.0 times 10 to the 5th power k. And this is my equation of acceleration. Okay, so now we can find the force because they say what are the components of the force acting on this proton. So if I know the acceleration, I know the second Newton's law. Say that the force, and that force acting is equal to the product of the mass times the acceleration. So the force here will be equal to the mass of the particle. There is 1.7 times 10 to the power of negative 27 kilograms time 0I minus 4.0 times 10 to the fifth J minus 8.0 times 10 to the fifth K. Remember that this expression over here is in meters per second square, as well as this other here is in meters per second. So we're multiplying kilograms times meters per second square, so it will be newtons, of course. So now we know that the vector force here will be, when we multiply, should be 0I 1.7 times negative 4, it will be negative 6.8. 10 to the negative 27 times 10 to the fifth is going to be 10 to the negative 22 J. And now 1.7 times negative 8, it will be negative 13.6 times 10 to the negative 27 times 10 to the fifth will be 10 to the negative 22 K. And it's a 4, so it's in newtons. So this is my equation, for the force. Okay, so basically the I component is 0. So this is a force that is in the YZ plane. Now they ask you to find the magnitude of the force. So if we find the magnitude of a vector, you know that the magnitude of this vector f would be the square root of fx squared plus fy squared of fz squared. So it will be square root of 0 squared plus negative 6.8 times 10 to the negative 22 squared plus negative 13, sorry, plus negative 13.6 times 10 to the negative 22 square. So this would be, if you do the calculation, equal to 15.2 times 10 to the power of negative 22 newtons. Well, basically, this will be 15 times 10 to the power of negative 22 newtons. Or 15.0 or 15.2 is going to be okay. So this is the magnitude of the force acting on this proton that is moving in an electric field. Sorry. So we found the equation for the force, and we found the magnitude of that force. Our second problem now here says that a boat is tied to a dock by 4 ropes, 2 ropes with a tension of 260 Newton each at right angles to the dock, and 2 other ropes with a tension of 360 Newtons each are at an angle of 20 degrees with the dock. So what is the resultant of those forces? So basically here we're making a representation. Uh, this is our boat, and here we have, the ropes, the 4 ropes in blue and green, tied to the dock. So, which are the forces we have here? If we analyze the forces, we're going to have a force of tension acting in this form, in that rope, another force acting here, another force acting in this form, another force acting in this other form. So those are going to be the forces. Let us call these forces F1, F2, F3, and force 4. Right? Now, let us just make a free body diagram of this. So we're representing my both point, okay? And then I will just make a coordinate system here. Let me use another color. This is my coordinate system X and Y. So I have my force F1, that is a force of 260 newtons, pointing to the right in the direction of the x-axis. And I have the force F4, that is also in the direction of the x-axis of 260 newton also. And now we have a force here, that is force F2. Let me use the color for these other forces. And the force F2 is making an angle of 20 degree, 20 degree with respect to vertical, and have a magnitude of 360 newtons. And we have this force also making an angle of 360 degree, 20 degree, and 360 newtons. It's evident that the forces of 260 newtons only have components on the x-axis, so they are just on the x-axis. But the forces of 260 newtons have components on the x-axis and components on the y-axis. Now, when you think a little bit about those forces of 260 newtons, the y component of those forces have the same magnitude and are opposite direction, so those y components are going to cancel each other. Nevertheless, the x components of the forces of 260 newton are both pointing to the right, so are going to be added to the forces of 260 newtons. So let us just make a calculation to show you, what is going to be the resultant in y. You're going to see how it's going to be equal to 0. So the resultant force in y will be the projection of this force of 360 newton on the y-axis. So this side here is adjacent side to the angle, so it will be cosine of 20. So I have 360 newtons. I will put this positive because the component is going to point up. 360 newton times the cosine of 20 degree minus, because now the component, the y component due to the force will be in the direction of the negative y-axis, so it will be 360 newtons cosine of 20 degree, because it's exactly the same angle for both. So it's evident that the resultant in y is equal to 0. Now we can find the resultant of the forces in x, and we have these two forces of 260 newtons. We have now the x component of the forces of 260 newtons. This component over here is opposite side to the angle of 20 degrees, so will be affected by the sign. So you can say, plus 360 newtons sine of 20 degree plus 360 newtons sine of 20 degree. So Rx will be in this case equal to 766.25 newtons, or you can round these and say there is 770 newtons. In what direction? To the right. Or using the unit vectors, you can also say that these resultant are x. When I use the direction, I can just write this as a vector. We can say that Rx, the resultant in the x-axis is equal to 770 newtons I, because it's in the direction of the x-axis. So this is as you see, it's a very it's a problem. It's a very simple problem. Just with your knowledge of trigonometry, you will be able to solve any problem like this. In our next problem, they say that two heavy boxes of masses to 20 kilograms and 30 kilograms sit on a smooth frictionless surface. The boxes are in contact, and a horizontal force of 60 newton pushes horizontally against the smaller box. So what is the acceleration of the two boxes, right? What is the force that the smaller box exerts on the larger box? What is the force that the larger box exerts on the smaller box? So this is just the problem. So we have the representation of the two boxes resting on a frictionless surface, right? And a force of 60 newtons applied over the box 1, that is going to be the box of 20 kilograms. So if I want to find the acceleration of the two boxes together, right? We can use the first Newton law. We say that the force is equal mass times acceleration. So the acceleration is equal force divided by the mass. In this case, what is going to be the acceleration? The force divided by the mass. So the force is 60 newtons. Divided by the mass, there is 20 kilograms plus 30 kilograms. So it's 60 newtons divided by 50 kilograms. So the acceleration will be 1.2 meters per square seconds. In the same direction, that we have the force F, that is a force pointing to the right. So acceleration points also to the right in this case. So we found already acceleration. Now the one that we find, what is the force that the smaller box exerts on the larger box. So to solve this second part of the problem, we're going to isolate the second box, right? And when we isolate the second box, we say, okay, my second box is a box resting here. This is smooth and frictionless surface. And then we know that the mass of this box is equal to 30 kilograms. And from the first part of the problem that we already solved, we know that the acceleration of this box is to the right, and the acceleration has a magnitude of 1.2 meters per second square. We know that there is a contact force here, that this is the force that the box 1 exerts in the box 2, on the box 2. So this F12 will be the contact force. So it's going to be the force that the smaller box exerts on the larger box. This will be the only force acting on this box because there is no friction. So we can say that the force 1 on box 2, the force that exerts the box 1 on box 2 is equal to the mass of 2 times the acceleration. So it's equal to 30 kilograms uh, 30 kilograms times the acceleration, that in this case is 1.2 meters per square second. So it would be 36 newtons to the right. So now we found, the force that the box 1 exerts on box 2. Now they ask you to find the force that the larger box exerts on the smaller box. So these boxes are in contact. There is no third box here. Okay, so what we're gonna have here is an action-reaction pair. So if the force 1 exerts, if the box 1, exerts a force of 36 newtons to the right on box 2, as it's an action-reaction pair, according with the third Newton's law, we're going to have that the force that the box 2 exerts on box 1 is also force of 36 newtons, but with an opposite direction. So it will be a force pointing to the left because it's same magnitude and opposite direction is an action-reaction pair there. So we found also, what is the force that the larger box exerts now on the smaller box. Next problem is a problem where we have a mechanic that is testing the tension in the fan belt by pushing against it with its thumb. The force of push is 130 Newton. It's just the force we are representing here in red. And it's applied at the midpoint of a segment of belt that have 46 centimeters long. The lateral displacement, so it's just how in this direction the belt is displaced at the point of the push, right, is 2.5 centimeters. So the question is, what is the tension in the belt while mechanic is pushing? Well, the first here would be to make a dimensional, analysis of the dimensions, right, of the parts involved here. I don't want that you confuse this analysis of the dimensions, or analysis of the geometry with a dimensional analysis that that is related to the units, right? So it's a analysis of the geometry, that we have in this problem. So let us say that this here will be this line will be representing, the belt when there is no push, right? So the belt when no push there. is going to be straight, okay? But due to the push, right, the belt really uh, take this geometry. I'm going just to make it more pronounced, more bigger, just in order to make it easier to visualize this. So we have this that we call the lateral displacement, and this lateral displacement, there is this distance over here is 2.5 centimeters. At the same time, we know that from this point over here to this point over here, we have that the length of the belt is 46 centimeters. So if I divide this into triangles as I am pushing in the exact middle of the belt, exact middle of the length of 46 centimeters, I can say that this dimension is the dimension equals to 23 centimeters. So basically, what we have here is a triangle like this, a right triangle with 23 centimeters here, 2.5 centimeters here, and it's important to find the angle theta, right? So of course, this here will be the hypotenuse, and these two are laps of the triangle. So theta will be the tangent inverse of 2.5 centimeters over 23 centimeters, right? This is tangent inverse of the opposite over the adjacent side. Cancel the centimeters out, we divide 2.5 by 23, and we find the tangent inverse, and we have that theta is equal to 6.2 degrees. So we found this angle over here. Okay, there is the same this angle over here. Why is important to know that angle? Because when we know this angle, now we can just put together the pushing force and the tensions, on the belt at this point, right? So we can make a diagram of the forces. We made these diagram of forces. We're going to have, and let me again, do some auxiliary lines. So I have the force of 130 newtons in this direction. This is the pushing force. And now we have the tensions. Let me raise this tension here to represent it with more or less the same angle. This is exactly, they have exactly the same angle. So we have the tension here. And we know that this angle is 6.2 degree, and this angle is 6.2 degree. Okay. We're going to rotate a little bit our coordinate system to make this easier. This is something that we do a lot of times. So we move the coordinate system. We rotate the coordinate system a little bit to align it with the system of forces that we have. So with this coordinate system over here, the y components of the tension are going to be the components, the projection of the tension force on this line. This will be the y component of the tension. They cancel each other. And the x components of the tension that are lying on this axis are pointing in this direction, so in the positive direction of the x-axis. These x components of the tension are two components that have both the same direction, have both the same magnitude. So if I make a sum of the forces that are acting on the x-axis, I know that I have 2 times the tension. The component lying here on the x-axis is a component that is opposite to the angle of 6.2 degree, so will be affected by the sign. So it's 2t, 2 times the tension times the sine of 6.2 degree. Now the pushing force is in the opposite direction, so this is a minus 130 newtons. We have no more forces acting there, so now we can say that 2t sine of 6.2 degree is equals to 130 newtons. So t is equal 1, so this is newtons, is 130 newtons divided by 2t, divided by 2 sine of 6.2 degree. And 130 newton divided by 2 sine of 6.2 degree, it would be approximately 602 newtons. So what is going to be the magnitude of the tension force? The magnitude of the tension force in this case would be equal to 602 newtons. In my next problem, I have a 220 pounds man that is standing on the scale in an elevator. So they say, what does the scale read when the elevator accelerates upward at 1.6 meters per square second? What does it read when it's accelerating downward at the same rate? So let us see here, what happened with what we call the apparent weight, okay, when you are in an elevator. So the first case is when the elevator is moving upward. So this is my elevator, and this is the person that is just standing here on the elevator. Now, what happens here? We have an acceleration upward of 1.6 meters per square seconds. What else? We have the weight of this person that points downward. And we have the normal force that is opposite to the weight. So if I say that the sum of the forces here is equal to mass times acceleration, let me put in black this here. The sum of the forces is equal to mass times acceleration. I can say here that the normal force minus the weight is equal to mass times acceleration, right? In this case, the acceleration is positive because it points up. Now let me make a conversion very quick because I have 220 pounds. So to convert these 220 pounds into kilograms, I say 220 pounds times approximately 0.4536 kilograms per pound. This will be approximately 99.8 kilograms, right? So now I know the mass of this person in kilograms. It's important because uh, we are working the International Systems of Units. So I will find the normal force. So the normal force, solving for normal force will be mass acceleration plus W. W is mass times gravity, is the weight. So normal force is mass acceleration plus mass gravity. Factoring the mass out, we have that the normal force is equals mass times acceleration plus gravity. So the normal force is equal to the mass. There is 99.8 kilograms times the acceleration, that is 1.6 meters per second square, plus the gravity here, that is 9.81 meters per second square. So when you find the normal force, right, this will be equal to 1,139 newtons. It's going to be in scientific notation 1.14 times 10 to the power of 3 newtons. So what I want you to see here, if the elevator is moving with uniform motion, or if the elevator is at rest, the scale will be reading uh, 99.8 kilograms times 10, approximately 10 meters per square second. So most of 998 newtons, right? This will be the weight. But as the elevator is accelerating onward, we have to add acceleration of the gravity with acceleration of the elevator, so the apparent weight of this person is greater than the actual weight, due to the acceleration of the elevator over. Now let us analyze what happens downward when the elevator is going downward. So in our second case here, we have this same person in the same elevator. The only difference is now the acceleration is downward. It's the same magnitude, 1.6 meters per square seconds. So we still have the same weight acting downward here, and we have the same normal force acting upward. If we make the sum of the forces in y, again, equals 0, equals to the product of the mass times acceleration, because it's moving with acceleration. We say, okay, again, taking positive, those forces that point up, I can say that the normal force minus the weight is equal to the product of the mass times acceleration. So the normal force is equal mass acceleration plus the weight. So the normal force is equal mass acceleration plus mass times gravity. Normal force is mass times acceleration plus gravity. But now we have that this part is negative because acceleration point downward. So even better, that to do at this point, I can just say here much better that this will be negative because we have a negative acceleration is point downward. And here we are taking, the weight downward. Also, the gravity, because the gravity is point downward, so there is no contradiction with the signs. What happens is that when we solve for the normal force, we bring this term out into the other side. So it's not a big problem. That means it's really negative in the sum of the forces, right? But when we isolate the normal force, it goes positive to the other side. So let us say over here minus mass times acceleration plus the weight. It's going to be the same. Normal force is mass times acceleration plus mass times gravity. So the normal force is mass times minus acceleration plus gravity, or gravity minus acceleration. Normal force is replacing the variables by the values. We have the mass, there is 99.8 kilograms. Minus 1.6 meters per square second plus 9.81 meters per square second. If you do the calculation, you know your normal force here is 819 newtons, or we can say that this is just 8.20 times 10 to the second newtons. So this would be the normal force. As you can see, the apparent weight. Now, when the elevator is going downward, is lower than the actual weight of the person, right? It's because we are subtracting the acceleration. So these problem of elevators are really very interesting, and you can do the experiment uh, if you live in a building. You can do the experiment with an elevator and one scale, you know, those that we use to keep a control of our weight. Let us analyze one more problem. They say a woman pushed horizontally on a wooden box of mass 60 kilograms sitting on a frictionless ramp, inclined at an angle of 30 degrees. So just draw the free diagram for the box and calculate the magnitude of all forces acting on the box under the assumption that the box is at rest or in uniform motion along the ramp. So let us see this problem. The first they ask you to do is to go with free body diagram, you know. So I'm going to represent here the box on the inclined plane. So what forces we have here? We have the force F that points in this direction here. We have the weight that points vertically downward. Sorry, this is not vertical. And we have the normal force that is perpendicular to the surface of the inclined plane. As you can see here now, I will be taking this axis as x-axis, this one as y-axis. I'm going to do something similar to what I did before on one exercise, that is to rotate the coordinate system to align it with the inclined plane. And then now I know that the force F and the weight are going to have components of my x and y axis, you know. So I'll represent also the components, right? We're representing my box now with a dot. So this is my y-axis, this is my x-axis. Okay, so I'm gonna have the weight that is vertically down. The angle of the weight with respect to the y-axis here is 30 degrees. and then the weight have an x component. We're going to call Wx, and it's going to have a y component. I'm going to call Wy. We have the normal force that is contained by the y-axis. It's over here. And then we have the force F. There is let us say there is acting at this point now here. Okay, and the angle of x here is 30 degrees. We spread the x-axis, and then we're going to have an x component of the force F. So this will be Fx. And we're going to have also a y component of the force F. That's going to be Fy. So those are all the forces that are acting on this system. Now I can start writing, the components according with the angle. So I can say now here that Wy, there is this component over here, is adjacent to the angle of 30 degrees. Remember that this here is the weight, and this is the angle of 30 degrees. So Wy is adjacent side to the angle of 30 degrees. So now we know that Wy would be W as is adjacent cosine of 30 degrees. Wx, in the other hand, is this one, so it would be a component that would be this other part. That means in this direction here. So it's going to be the opposite side to the angle of 30 degrees. So Wx is W sine of 30 degrees. We do the same for the force F. So Fx, there is this component over here, is adjacent side to the angle of 30 degrees of F respect the x-axis. So Fx is F cosine of 30 degrees. And then Fy, it's going to be the same, that this segment here would be opposite to the angle of 30 degrees. So Fy would be F sine of 30 degrees. Now the normal force would be equal to the sum of Fy and Wy. So the normal force is Fy plus Wy. So the normal force would be F sine of 30 degrees plus W cosine of 30 degrees. So I found here, the different forces. Now I'm going to calculate the magnitudes. So what I know that the mass of the box is equal to 60 kilograms. Let us measure. 60 kilograms. Okay, this body over here. This is the mass of the box. So the weight, that is mass gravity, 60 kilograms times then 9.8 meters per square second. So this would be 588 newtons. This is the weight. Now, once I know W, I'm ready to find Wx and Wy. So Wx is W sine of 30 degrees. So it's 588 newtons sine of 30 degrees. So the sine of 30 is 1/2, so this will be 294 newtons. You can find Wy, there is W cosine of 30 degrees. That is 588 newtons cosine of 30 degrees. This will be 509 newtons. What else? We can now find the forces. In this case, we know that Fx is going to be equal to Wx because those are the only forces that we have on the x-axis. So Wx and Fx are equal. They are just the only two forces projected on the x-axis. Remember that this is a rest or uniform motion, so there is no net force on the x-axis. So we can say here that Fx is equal to Wx. Is equal to 294 newtons. Once I know Fx, I can find the force F, because I know that if Fx is F cosine of 30 degrees, Fx over the cosine of 30 degrees will be F. So it will be 294 newtons divided by the cosine of 30 degrees. So that will be 339.5, so it will be approximately 340 newtons. So F is 340 newtons. Now we can find Fy, because we say that Fy is F sine of 30. So it's 340 newtons sine of 30 degrees. So it will be, in this case, 170 newtons. We found also Fy. And finally, we have to find the normal force, and we know that the normal force is Fy plus Wy. So it will be, in this case, 509. We can round this to 510 if you want, just 509 newtons. That is Wy. Let me just put in the same order that I wrote the terms in the formula. So Fy 170 newtons plus Wy. Wy we said there is 509. Newtons. So the normal force will be 680 or 679, so approximately 680 newtons. So we found the magnitude of all the forces. So the analysis of the geometry is always very important in these problems. Okay, so you need to look for all those knowledge you have, this knowledge you have about trigonometry in your mind, and you have to pull that knowledge again and activate it to be able to solve these problems. So I hope you know that this group of problems are going to help you to understand better this topic. And well, I wish you, success in the solution of the exercise of this topic. Thank you for your attention.